All right, thank you. I'm here to talk about post-Chicxulub radiation and dispersal of Amphisbaenia. So to summarize what I'm going to talk about here today, the worm lizards, or Amphisbaenia, are a specialized group of burrowing lizards that live as subterranean predators. The Amphisbaenians are widespread today on either side of the Atlantic Ocean. They're found in Africa, South America, Europe, and North America. And this has traditionally been explained in terms of continental drift. My colleagues and I tested this hypothesis using a combination of fossils, phylogenetic analysis, and molecular clock analysis. And what we're going to see is that the standard explanation is wrong for worm lizards, and I'm also going to argue it's not just wrong for them, it's wrong for a lot of different things. So in recent years, I've become interested in the squamates. These are the lizards and the snakes. This is a very diverse clade. It has roughly 9,000 known species. They're ecologically diverse. There are insectivores, there are carnivores, there are herbivores, and they have a wide range of lifestyles. Some are nocturnal and some are diurnal, some are terrestrial, some are arboreal, some are aquatic, and some are fossorial, such as these worm lizards here, which are specialized for subterranean existence. Now, recently, my colleagues and I got interested in looking at squamates in the context of the end Cretaceous mass extinction. So the KT, or now KPG mass extinction, is, of course, a severe, global, and rapid extinction event. It's estimated to have eliminated upwards of 75% of all species on Earth, making it the most severe extinction in the past 250 million years. The most famous victims of the extinction being, of course, the dinosaurs. And it coincides precisely in time with the deposition of the iridium-enriched boundary layer left by the Chicxulub asteroid impact, suggesting a causal connection between Chicxulub and the extinction. Now, traditionally, it's been assumed that this had relatively little effect on the smaller members of the fauna, such as the lizards and snakes. Recently, I worked on a study with a couple of colleagues looking at this, testing this hypothesis, whether lizards were in fact uninfected by this event. And we looked at lizards from and snakes from the latest Maastrichtian of Western North America, and we found unappreciated diversity there, and we also found overlooked extinction. What we found is an extraordinarily severe extinction of lizards and snakes. In the late Maastrichtian, we have 30 species here. We found that of those, only 5 crossed the KT boundary. The remaining 25, 83%, became extinct at the KT boundary. We also saw, this is just species level, we also saw entire clades disappearing at this time. So this event had a really severe effect on lizards and snakes. So why does this matter? Well, I'd argue that the Chicxulub mass extinction is a form of creative destruction, that it really drives the evolution of modern lizards and snakes and also the biota as a whole. So the origin of the modern biota, maybe we need to understand the mass extinction event to understand where it comes from. And looking at the fossil record, it appears that a lot of the modern lizard and snake groups, things like agamas, things like iguanas, things like boas, things like venomous snakes, they all have their earliest appearance in the Paleogene after the extinction event. And this suggests that maybe the diversity, and I'm going to argue possibly the biogeography of these clades, is driven by this end Cretaceous mass extinction. And we can look at fossils to test this idea. So we set up this idea that this mass extinction might be leading to radiations and evolution in the aftermath, but we didn't really have a lot of fossils to test it. So the group we decided to look at was the Amphisbaenia, or worm lizards. So what is an Amphisbaenian? Amphisbaenians are a really weird group of animals. They're moderately diverse. There's around 200 species in 6 families, and they're extremely specialized for a subterranean existence. They have these long worm-like bodies with these sort of rings of scales, just like an earthworm, and they can use an accordion-style locomotion. They can't lengthen their body like an earthworm because they have a spine, so they slide the skin around their spine just like the loose sleeve of a sweatshirt to crawl underground. They have highly reduced eyes because it's dark underground, but their ears are specialized to detect subterranean vibration of buried prey, and they have these massive jaws and teeth to seize and tear their grub and worm prey. So this is a really weird group of animals, but one of the weirdest things about them is their biogeography. So they're widely distributed. They're found in North America, South America, Europe, and Africa. So how is it that a group of animals that is confined to burrow systems is somehow so widely distributed? So the traditional explanation of biogeography was the was the dispersal hypothesis developed by Darwin and Alfred Russel Wallace. And they proposed that animals migrated to their current habitats from either via ancient land bridges, such as the Bering Land Bridge, or else rafted there, such as the turtles and iguanas rafting from South America to the Galapagos Islands. And these dispersal events were very, very improbable events, especially the rafting events. But in the absence of any other mechanism to explain biogeography, they were the only explanation that Darwin and Wallace had to work with. Things changed a lot in the 20th century with the development of plate tectonics, of course. If we have this giant supercontinent Pangea where all continents are linked together and it slowly splits apart until by the mid-Cretaceous we have the formation of the Atlantic, you can imagine a situation where a group of animals, such as the Amphisbaenians, could be widespread 200 million years ago, and then as the continents slowly split apart, they simply passively ride to their current locations. So this seems like a very plausible mechanism for explaining the distribution of a clade like the Amphisbaenia. It doesn't seem to have a lot of dispersal potential. And this was the favored hypothesis for a long time. They were a very ancient group and simply rode along with the continents. This hypothesis makes it a testable prediction. If they are in fact distributed via vicariance, this has to be a very ancient group because this happened a very long time ago. So recently there were some molecular clock analyses run on the Amphisbaenians. They found something rather surprising. They found that the Amphisbaenian crown as a whole, the Amphisbaenia, originate around about 100 million years ago, or a little older, in the early Cretaceous. So the clade itself is fairly old. But the main pulse of Amphisbaenia here, this group called Amphisbaeniformes, they found originated around about the Paleocene-Eocene boundary, about 10 million years after the Chicxulub event. And that makes this major pulse of radiation, which is the most widely distributed group, relatively recent. And they argued the only way you could have this recently evolved group being widespread was via oceanic rafting. And they suggested there must have been long-range rafting across the Atlantic to explain the distribution of this clade. And it seems absolutely fantastic. How do these tiny little subterranean burrowing lizards somehow cross vast oceans? And one issue with this analysis is that they only included a single molecular calibration, single fossil calibration for the Amphisbaenia in their analysis. So we decided to use fossil Amphisbaenians to kind of test this idea. And I will show you how this ties back into extinction as well towards the end of the talk. So this was sort of born out of the extinction study. Is in the process of going through these collections in the museums, I ran across this odd little jaw mixed in with a bunch of salamander jaws at the American Museum of Natural History. It's very, very short, very deep, and has a few very, very large teeth and this weird sort of V-shaped symphysis. And all of these are classic Amphisbaenian features. And this turns out to be the oldest Amphisbaenian, and by a couple million years, and one of the most primitive known Amphisbaenians. And it's a new family that is the only example of this family. And curiously, it occurs almost immediately after the Chicxulub impact. It's occurring probably within a few thousand years of the Chicxulub impact, just in the earliest Paleocene. Going through museum collections, we also looked at some other Amphisbaenian fossils that have been collected and identified a long time ago. This thing here is a different family called the Rhinuridae, found in the early Paleocene in Wyoming, in North America. Again, here's another thing. This is a family called the Oligodontosauridae. And there's some debate as to whether this actually was an Amphisbaenian. It turns out it probably is. Again, North American, early and in the early Paleocene. And then going to the literature, there are a number of other Paleocene Amphisbaenians out there. And what we've got is we've got this thing in Europe, and we've got this thing in the late Paleocene in Africa. So based on the fossils, it appears that this major pulse of radiation is not happening at the Paleocene-Eocene boundary. It has to be happening a bit earlier, probably in the early Paleocene. And a literal reading of the fossil record seems to suggest that this clade is suddenly becoming very, very diverse after the Chicxulub impact. The question is, of course, is that just a sampling artifact? Have we not found all the Amphisbaenians out there in the Cretaceous? And this is where molecules come in, as we can use the molecular clock to figure out when this group originated. So my colleagues and I decided to try and combine a bunch of different data sources. We combined molecular data here A's, C's, G's, and T's. I forget what gene that is. It might be 12S or something. We looked at some CT scans of modern taxa, and then we looked at the fossil things to try and figure out the phylogeny and the timing of origin of this clade. So first of all, we did a molecular analysis. I can't remember all the genes we used offhand. It was things like CMOS and BDNF and 12S. But anyway, we got genetic sequence data downloaded for all the taxa we could find in modern taxa, and came up with this as we think, a fairly robust hypothesis of the relationships of the modern taxa. And we basically use this as a backbone for interpreting the fossils. So using this as a framework, we were able to slot in based on the morphology, the placement of the fossil taxa. And so we have these guys here, and they contribute important information about the geography of these guys. So we have fossil taxa here: North America, North America, North America, Europe, and Africa. But critically, in addition to providing information on the position and space of the radiation, they tell us about the timing of the radiation. So now all of these guys can be used as calibration points in a molecular clock study. So we did a molecular time tree, and this is the result of an analysis in the Bayesian analysis using the program PhyloBayes, using the CAT plus GTR plus gamma molecular model. And this is what we got. So we did get an early Cretaceous radiation of Amphisbaenia before the continents have fully split up. So the most ancient lineage, this Rhyneuridae, kind of split off a long time ago. However, we get, consistent with the other molecular clock, we get a major pulse of radiation here in the Cenozoic. These Amphisbaeniformes are diversifying after the KPG boundary. The main difference between the previous study and our study is we get this happening about 10 million years earlier. So instead of happening at the Paleocene-Eocene boundary, what we're seeing, because we have these additional molecular calibration points, is the radiation is happening almost immediately on top of the KT boundary. We get it at 65.5, just 500,000 years after the Chicxulub impact. And so this is consistent with the post-Chicxulub radiation of this clade, as we were proposing was likely to happen given this mass extinction of lizards. So this is what everything looks like if you combine everything together. This is combined morphological, molecular, and fossil data. We have crown amphisbaenians originating here in North America. There's the final split up of Pangea as the South Atlantic forms. And then we have this major pulse of radiation here. And at the same time we get this pulse of radiation, we're also seeing dispersal events. So this event here is dispersal into Europe. This event here is dispersal into Africa, dispersal into the Caribbean, dispersal again into South America, and then dispersal into the Caribbean. A series of dispersal events in the Paleogene concentrated just above the KT boundary. So this is how this looks mapped out. We have one dispersal from North America to Europe in the early Paleocene, a second into Africa, Caribbean, South America, and again into the Caribbean. All this dispersal happening in the Paleogene. So what we're finding in this clade is that we have not vicariance, but dispersal. So how do you get these worm lizards across oceans? The most likely hypothesis, I think, is that they're basically passengers in soil carried by tree roots. Either individual trees that have fallen off of cliffs or been washed downstream by floods, or in the tropics you have rafts of vegetation. You can have a whole stand of trees 20 or 30 feet across, ripped up by a flood and carried downstream by these large floods in the Amazon. And with good prevailing winds and currents, these things could take several weeks to cross an ocean. These are extraordinarily unlikely events, but they're the only real explanation. And another thing that's worth thinking about is that over the course of millions and millions of years, these once every million year events will happen by definition many times. So, dispersal versus vicariance. So I've shown that this really bizarre clade owes its distribution to dispersal rather than vicariance. Is this a normal pattern, or is this just a weird clade? Do they really tell us anything about evolution? I'd say if you look at other groups, you find very similar patterns. Iguanas are a Cenozoic radiation, primarily in the New World, but there are a couple of oddballs. There's one group in Madagascar, and there's one group in Fiji. So how do you get iguanas into Fiji? You have to raft them there. They've never been in Asia. So these guys have to somehow raft across something like 8,000 kilometers of open ocean from the Americas to colonize Fiji. To get iguanas into Madagascar, you'd have to raft around 10,000 kilometers a day, probably less back in the Paleocene, but still a really long distance. So, okay, maybe lizards are really weird. Maybe they don't really tell us a lot about biogeography. Well, again, if you look at other clades, you'll find that a lot of these clades tend to be very, very recent in origin. So this is a really recent molecular clock for the mammals. And you see that the crown orders all diversify after the KT boundary. If these groups are diversifying after the KT boundary and colonizing isolated land masses after the KT boundary, like Africa and South America were, then you have to invoke dispersal events. And so to explain the origin of rodents and primates in South America, for example, from Africa, you have to have a rafting event across the Atlantic. Likewise, the fauna of Madagascar has to raft to colonize Madagascar. Australia, again, you have to raft to get there. So even mammals which don't seem like they'd be well suited to rafting, you have to invoke rafting to explain how they got to their current distributions. Birds, of course, there's very little reason to expect vicariance. For one thing, they can fly. You don't really need to invoke any sort of vicariant models for this. The other issue is, of course, that you have a major pulse of radiation after the KT boundary. So again, these guys are originating quite recent. Break of Pangea is finished by about 95 million years. These guys are diversifying at 65 million years ago. So, what I'm going to argue here is that the fossils provide us with critical data, not just about when things happened, but about where things happened. And this is really critical to understanding biogeography. And these Amphisbaenians give us some new hints about how this radiation played out. The fossils tell us they're coming out of North America and when they're coming out of North America, which is really useful for reconstructing the biogeography of this clade. And the Amphisbaenians and the fossils and the molecules all taken together provide a scenario that's very consistent with the classic hypotheses of Darwin and Wallace, where we're invoking events like land bridges and oceanic rafting to explain the origin of the clades. And I'd argue that this is probably not the case only with Amphisbaenia, but most things out there. If you wipe out 75% or 90% or however many of whatever percent of all species on Earth at the KT boundary, most of the diversity and the biogeography has to be built up since then. So I think whatever vicariant patterns might have been existing at 95 million years ago have largely been overwritten by the KT extinction and subsequent radiations. And it might work for a couple of oddball taxa like lungfish, but I'd say that for the most part, vicariance is an explanation that's simple, it's intuitive, and it's wrong. It probably happens with a few oddball clades, but I think it's basically a myth. And that line did not go over well at the Hennig conference, as you might guess. So, what role does extinction play in this? I think that extinction counterintuitively might play a really important role in understanding biogeography and driving biogeography. So why are Amphisbaenians suddenly dispersing after the KT boundary? I don't think it's changing the odds. I don't think it's changing the odds of a successful dispersal event in terms of changing the probability of a rafting across the Atlantic. The physical barriers probably remain about the same. However, a dispersal event not only has to cross that ocean, it has to then become established. And that second part, the establishment of a lineage, once it crosses an ocean, is a really critical part of the colonization event. And there is what I'd call a biotic barrier to dispersal. Once you colonize new habitat, there's predators there, there's competitors, and extinction events remove these, and they make it easier for you to colonize new habitat. So I'd suggest that I'm throwing up a hypothesis that maybe extinction events make dispersal more likely by wiping out predators and competitors. So, final slide to summarize. Lizards experienced a mass extinction 66 million years ago as a result of the Chicxulub impact. This is followed by radiation and dispersal in the aftermath, as exemplified by Amphisbaenia. These patterns are probably not unique to Amphisbaenia, but probably characterize other groups of vertebrates, invertebrates, and plants as well. And I'd say Darwin and Wallace were probably right. Dispersal is the primary process explaining biogeography, and that extinction induced by events such as asteroid impact, volcanic eruption, and climate change may drive dispersal by creating ecological release. So I'd just like to thank you guys for listening and thank all my colleagues and collaborators.